Ladies and gentlemen, good morning. Welcome to Blink Innovation. Welcome to Lincoln University. And welcome to this innovation series talking about computer vision on farm. When I discussed this with the team to put this subject on, I said, well, that's basically talking about something that hasn't changed. Because when my grandpa was going to check his crops, he would get up early in the morning, he would walk his field, and after he would come back, he would have breakfast, and we would discuss what we were going to do for the rest of the day. The only thing that has changed is a skill. We no longer have a small little field that we can actually walk before breakfast and then decide what we're going to do the rest of the day. We have hundreds of hectares. And suddenly, then computer vision comes into play, because computer vision can do it much quicker. But also, with different sensors, they can see more than our eyes can actually see. So, yes, everything has changed. So that's why we are very happy that you are here to talk about computer vision on farm. My name is Wim de Koning. I'm a member of the Blink team, and the Blink team is actually welcoming you here to Lincoln University. And thank you very much. Before we're going to start, a little bit of housekeeping. We do not expect any fire drills. So if we have if we hear the alarm, it is for real. And luckily, you're in really good hands with the B-Link team. So we will actually escort you out to the gathering area. There are exits here on the back. The door that you actually came into is an exit as well. And for those of you who have already walked towards the toilet, you would have seen that there are exits to your left and your right as well. The toilet is actually going out the hallway, and then it is a door on your right-hand side. I do apologize. Yeah. And I think for the people at home, because we're live streaming this, welcome as well for you at your behind your computer screen or television screen. I hope that you will find your own emergency access if there is an emergency in your area. Yeah, for those of you who don't know what Blink is about, B-Link is a business unit of Lincoln University, and we basically do three things. We really bring people together, like we do today. And we really hope that we actually will start connecting people. So start to talk to your neighbor and start to talk about what you guys do. And hopefully then you get interested and say, well, perhaps we need to talk a little bit further and we need to talk a little bit more. And then actually collaboration starts. And we are a true believer that when that collaboration is synergetic, then the real innovation starts, and then it's based on a win-win for everybody. So that's basically what we do. It still doesn't work, Katie. May I have the next slide? So now, without any further ado, let's start with the session, the talks of today. So, computer vision on farm. May I have the next slide? We are a paperless office, so if you want to connect with us, or if you want to have questions, or if you want to further continue, please connect with us on social media, and we will be happy to communicate with you. Introducing our speakers. The format of today, what we're going to do is we'll have our speakers talk. After that is done, there will be a Q&A both here in the room as well as on Zoom. On Zoom, please use your chat function to actually give us your questions, and the B-Link team in the back of the room will actually moderate, and they will actually read out your question, and that's how the question can be asked. Of course, here in the room, we'll just put up our hands and I walk towards you with a microphone. We have three speakers today. There was going to be four. We had invited Craig McKenzie here as well, a farmer, or somebody active in the primary industry using precision agriculture on his own farm, but unfortunately he couldn't come today. So we are still very happy that we have 2 speakers from Ag Research and 1 speaker from Lincoln Agritech. I think that Seth and Remy are going to do a duo presentation. So I'm going to introduce both of them at the same time. I'm going to start with Remy. He's a landscape ecologist, and he specializes in eco-service mapping. So he is basically interested, how can we transform our current landscape in a sustainable landscape? And he is part of the Hyperfarm project of Ag Research. The leader of that project is Seth, and he specializes in soil and water dynamics. And he actually turns data into visualization, and with that visualization, he hopes that farmers can actually make better decisions on their land use. Seth and Remy.
Cool. Thanks very much, Vin, for the introduction, and thank you very much for the invite. What we've prepared today is we were asked to prepare 2 presentations. We thought we'd combine them because it seemed logical, and hopefully that makes sense as we go. So essentially what we're interested in is how we can use technology to accelerate change by better informing decisions that are done on farm. So we do a whole lot of science here, and there's quite often a slow or perhaps even a break in the continuity of that information to the people who actually make decisions on farm. So that's where we're interested in. We are driving a project called Hyperfarm. What we've done today is we've said, all right, well, we're going to take the particular things out of the Hyperfarm program that relate directly to the topic, which is visualization. Great, perfect. So the threats to us, or what are the threats that are actually happening on farm at the moment? There's a requirement for a greater consideration of biodiversity in the way that we farm. That's nothing, in fact, none of these should be new, but I'll go over them anyway. There's obviously a deterioration in the water quality that we're seeing around New Zealand that was largely dictated by nitrogen. It's also now encompassing sediment and phosphorus, particularly in the southern regions. And also we're seeing, situations like we had in Greymouth a few days ago, where we're seeing these large events happening, weather events happening more frequently and at greater veracity. So, and I tend to link that to a change in climate, as well as people are eating less meat, which is something that should concern us in New Zealand. Thanks, Katie. So I guess our hypothesis here is that the future is going to require a suite of things that we do on farm that will be new enterprises, or enterprises that are operating fundamentally differently to how they are now. That's not all enterprises, but there will be a significant shift to changing and more complex array of enterprises that we're doing on our land. And so the bit that we're interested in is, if that is going to happen, how do you get somebody from A to B? And what is the thought process that happens between A and B? Because those decisions are going to be very complex, and they're going to require a whole lot of considerations. And the last point there is essentially those considerations would be the environment, as well as the cultural, the social, and the financial implications of that change. So I guess underlying some of the work that we do is a hypothesis that multifunctional landscapes are fundamentally better for achieving a wider variety or a wider array of ecosystem services that we as owners of land would like, but also communities are expecting. So shifting from largely monocultural enterprises to multicultural enterprises is something that, in my view, is being driven from a large picture. How do we change a landscape, a catchment, into something more diverse with greater diversity of function in it? But I also believe that a lot of the decisions in us getting to there will rely on individuals. And the mechanism that we are using now primarily is the farm environmental plans. I think that life will change in that space, and I think they will become a lot more holistic in the way that they are intending to manage land through an agreement with the landowner. So this is if you go back to the first, not UKD, but if you go back to the first situation, oh, no, that's right, yeah. If you go back to the first situation where you have large, pivots of land. I've got nothing against pivots. I'm using this as an example, but this is what we've done on precision placement of water around a pivot. That's in the precision ag space. Essentially, I've put that slide up to say that's not really what we do. We are more looking at the next slide, which is how do we look at a landscape when your father goes out of them and says, all right, what are the things that we're doing today and what are the jobs that we need to do? How do we actually take a much bigger picture from that and say, all right, well, what are we trying to do in the next year here? What are we trying to do in the next 2 years? And actually, are we fulfilling what we want to do in our lives? It might be growing, I'm not going to say tulips, I'm going to say something much better than that. Carrots. Do we actually want to be growing carrots, or do we want to be doing something else? So how do we actually take those larger questions that we have that influence us, but they also influence our neighbours and the people around us, to achieve those larger objectives, right? So in this instance, how do we understand where, say, sediment is being lost, and then Katie, and then how do we grow some trees and understand what that does to sediment loss? So it's more in a predictive space than I think these two are not exclusive, they are complementary, but really what I'm talking about today is this predictive modelling and the interactivity that's required to achieve it. So next slide, thanks Katie. So essentially what we do, which is common across the precision ag, is we have essentially a geospatial grid. And that's great, there's nothing new there, but essentially what we are trying to do is place interactive features onto that geospatial grid. I want trees, I grow trees, how does that impact on my sediment? And what we're trying to do with that is to not only enable the science to be more readily accessible, comprehensible, but it's also trying to create an emotive connection to what we're depicting, essentially. Can I see myself growing apricots? Not really. Can I see myself growing asparagus? I like the look of asparagus from my kitchen window. It seems trivial, but these are issues that actually are driving decisions on farm, not the only decisions. So what we then need to do is bring in models and everything else into that geospatial grid to say, that's cool, you want to grow trees, your profit's going to be down $50 a hectare or $1,000 a hectare. So it's trying to standardize things onto a grid, but make them interactive. And this is a LiDAR image that we've created of one of our campuses down in Dunedin, and we've planted some trees on it. So essentially we can understand the impact of planting the trees. So the tool that we have created to do this, we spend a lot of time trying to work out what are the things that should be in this box. And through our development of now 3 tools, the things in that box have been small. The number of these boxes, sorry, have been small. Then there were heaps. There were lots of them, and we were really clever. And then we decided, actually, we talked to a whole lot of people, and we said, actually, people aren't using that information to make decisions. They're actually using this information. So we've gone back down to something more simple. So what's the message in that is science is one thing, but actually enabling people to access information and provide them the information that they want is it's not a completely different thing. It shouldn't be a completely different thing, but they're not the same thing. We need to understand exactly what information is required for the decisions being made. These are aggregated, but we can disaggregate those into nitrogen, phosphorus, and sediment, carbon emissions, finance, and land use suitability. And we've created a sort of a 3D terrain, which looks really cool, but it sort of enables people to visualize their farm a lot better. And what we do when we do that is we enable a lot of that tacit knowledge that people have in their head to be incorporated into the way that they're interacting with the tool. Katie. The tool that we have now just finished, finished its development phase. It's now ready to be soft rolled out. Is available anywhere in New Zealand. So while the LiDAR picture that I showed before is really good, if it's a one-on-one consultancy, that's great. It's very expensive. What we are trying to do here is enable that information to be accessible by many and cheaply. So we can pick up any site across New Zealand. Katie? And we've looked at one of the key challenges when we do that is to say, okay, well, what's actually on that land? What's on that land now? Because we need to have an understanding of where we're currently based. And Remy, do you want to jump in?
Yes, sure. So this is one of the challenges, as Seth mentioned, that we have raised by developing Hyperfarm. Here, what we want essentially is the user to spend the less time possible to input and map the current farm, the current land use on the farm. So we need to have a very good picture of what is currently happening on the farm. And what we did is we worked with Orbica and we developed a model based on data from the US to essentially map grape and apple across New Zealand. And the novelty here is we've proved that using US data with the knowledge transfer process and a small amount of New Zealand data could achieve a high level of precision in mapping those two land use in New Zealand, which is quite new and quite interesting because we have a very small database in New Zealand to train the model, and we can benefit from things that are happening elsewhere in the world where there are better databases.
And one of the questions we asked ourselves with this piece of work was, if we were to, say, look at sediment or nitrogen, how does having a more frequent map of land use with potentially a more frequent land use, that's temporal and spatial, how does that influence the model that it is being applied to? So does it influence sediment if we have a more up-to-date land use cover map, or does it influence nitrogen, or the both, essentially? So, so one of the challenges is in building this together is what I've said, is to understand what grows, but also what can grow. And here we've taken massive, massive data sets from all over the world, huge data sets for where cold climate apples grow, or a particular gala apple grow. We've then used a machine learning approach to understand the ecosystem that that apple is sitting in. So what are the terrains that it sits in? These are commercial varieties only. What terrain does it sit in? What rainfall does it sit in? What are the growing degree days, chill hours, and all the things that are influential for apples. We haven't said what those things are. We've just said, tell us what they are in all these places. And then we developed a model that said, all right, well, we know that gala apple are in these ranges. We're going to go and find these ranges in New Zealand. And so this is what we've done here. And we've done that for an apple grower now who's interested in a particular apple variety that will come from offshore to New Zealand. And they are looking for space now to maintain their license to breed that variety. We've also done that with Sauvignon Blanc wine. We've done it with all the wines, haven't we? But for Wine New Zealand, where we've said, okay, well, if we can develop the model that understands the environment where these particular grapes grow, and that's not necessarily where we are growing them now, that's where others are growing them, we can then understand where they are in New Zealand, but we can also then overlay a future climate onto that to say, all right, well, you know, geez, guys, you better start getting your production houses ready in Canterbury because that's where things are going to be moving to. Okay. One of the other challenges is that we've had is not everyone's out to achieve the same objective here. People have different objectives and things that drive them differently. So I want to understand what variety, what crops or land uses I have available to me if I am interested in water quality. So a contextual question might be, you have a limit of nitrogen, you are over that limit, you need to change some things. All right, what will I change? So, you know, it's trying to understand the particular pressures that a farmer might have and then addressing those. And then we can understand what the impacts of grapes on, say, for this instance, water quality. So we can say, okay, well, if we put grapes onto our land, what's the impact of that on our land? We did have this grid at 1 metre by 1 metre. We were paying $500 a month in data transfer, and then we aggregated it back up to a 1 hectare thing. So these are some of the learnings that we've had along the way past that are, you know, trying to, you know, that are essentially telling us what is the requirement here, what is the, you know, my supervisor used to say, the best thing a PhD student could learn is when to use a spade and when to use a spatula. So, cool, Katie. And then, as I said at the start, one of the important things here is the connectivity of people with the data. So here we've used visualization. We can currently take trees, 3D models of trees that look like apricots. They've got apricots growing on them. And you can say, well, actually, I don't really want that there because that's where my wife drives her car into the garage and it's going to shade it in winter. Okay, let's move them over there then. You know, and so there's an ability to visualize what that will look like in order to unlock that tacit knowledge to say, actually, I know it's always boggy in that paddock. No model's going to pick that up, but I know it's boggy, so I'm going to sort of incorporate that into the way that I'm shifting my trees around. And, yeah.
Good, awesome. So while we were developing the visualization within Hyperfarm with some 3D models of different land uses and 3D terrain to enable landowners to understand what the landscape might look like in the future and with different simulation of different land uses, we realized that it wasn't enough. So essentially, after discussing with a lot of landowners, we identified a need to better understand the aesthetic of planting trees within the landscape. And there is first there is a lot of confusion around the ETS system and carbon credit in New Zealand and how to do carbon farming. And on top of that, there is question about what can I, as a landowner, what can I see from this specific place in my farm if I plant trees? And we received a call from somebody in Taupo Regional Council, and essentially they had all the data ready, and they convinced a lot of landowners to plant trees on their farm from a science perspective. But they were struggling to make them implementing those plantings due to some visualization issue. People didn't want to plant any trees because they were unsure if they were planting trees how the view on the lake would be. So they didn't plant any trees, and they were stuck there. So visualization was a bottleneck. So based on that, we decided to push the visualization to the next level, and we used immersive technology to help landowners to visualize trees on farm. Thank you. So we took a case study in Banks Peninsula, and we worked with Raiwa Maori Trust on a 600-hectare beef and lamb farms. It's a good fit for us because in this specific location, this trust is trying to plant trees, but they don't know really where to plant them. From two points of view, the aesthetic point of view, but also from the production point of view. They want to keep some animals on the farm, and they don't know where it's better to keep animals and plant trees. So that's essentially illustrating the development of the VR prototype. So everything you are seeing here is accessible from a headset. So you are completely immersed into this technology. What we did is we used Sentinel-2 images, and we did a classification of pasture production based on images from 2019 during the lambing season. And we used MPI lookup table to estimate carbon sequestration in trees. So we have a linear relationship between the area of trees planted and the amount of carbon sequestrated. And according to where you are planting trees, so if it is in a high productive area or a low productive area, there is different impact on the carbon emission from the farm, and there is different impact in terms of profitability for the farm. And the same variation happens if you choose different type of trees. And we have three different type of trees. We have native trees, pine trees, and eucalyptus. So all of those things are combining together to essentially challenge the user to design a carbon neutral farm using the specific example I mentioned in the Banks Peninsula. So as a user, you will enter the game and you will start to plant trees with a seed gun. And as you are planting trees, you are getting close to carbon neutrality, but you need to maintain your profitability. So that's still images from the VR game. So as you can see here, there is different colors representing different pasture production levels. So the red is very low pasture production, the green is very high pasture production. So if you plant trees in a very high pasture production area, you will lose quite a lot of profitability because you remove the animal from the ground. But you will also lose a significant share of the carbon emissions because less animals means less emissions, so you get closer to carbon neutrality. And can you go back, please? And this here is an example on how we could use this type of immersive visualization for different purposes. And what you can see here are two whenua, so it's area of specific significance for the Maori Trust there. And they do not exist in the land currently, and they ask us to put them there and see what it would look like if they actually build those structures. Thank you. And so this is just to provide a comparison with something that we all know. So these are Google Earth images, and these are from the virtual reality game. And what you can see is the combination we have used between a 30-centimeter resolution aerial imagery for the landscape texture here, with a specific texture that we have built within the engine, which is a combination between soil and grass texture, provide a much better aesthetic and realism than Google Earth would be. And so this is to show that you have different type of trees. So you can see here the native trees, the pine trees, and the eucalyptus.
That's the...
Oh, yeah.
Katie, can you switch one more?
Yep, thank you. And this is a flyover a landscape that we have designed within the virtual reality game, essentially, but I'm not sure it is rendering well. If you guys want to experience that better, we can provide a testing one day.
I told Remy to bring the goggles,
Yeah.
but then we thought, oh, I might block things up. Right, cool. So essentially what I hope we've conveyed is, so we can certainly have another discussion at some point about all the science models that are going into this, but I think what we were trying to address today is the particular things around the visualization components that are coming into this objective and the sort of experiments that we've tried and come back on. We typically use a proof of concept approach in order to stage gate our development. But I'm certainly convinced that that if we are to achieve the landscapes that many of us are expecting, some of those decisions are extremely hard to make, and ultimately they probably will be made. But what we're trying to do is accelerate that process, and it's not. What we're essentially trying to convey here is that science is extremely important, as well as interactivity and visualization. So they are key components of this puzzle. But ultimately, they will not make the decision for us. They are essentially there to aid the decision making, but they're not there to say, right, well, the Hyperfarm says I should be growing grapes, so let's go get some posts and some grapes. So that's that. And typically in our work, we use a sort of a user-centric approach to things where we, build things, small things, work with people, understand what works, what doesn't work. We've sort of built quite a tough skin with, feedback, which is really good because that's extremely important to us. And then I think that's us. Yep, good. Thank you.
Thank you.
Thank you so much, Remy, Seth. Time for our third speaker. That is Jacco from Lincoln Agritech, and he's a machine vision specialist. So he's using computer vision, then takes it into imaging processing, and then looks at using mathematics, my favorite subject at secondary school, to make sure that he optimizes things for decision making. And the outcomes of his work will actually be seen in integration on field. Jacco, floor is yours.
Thank you. Good morning. I'm here on the campus of a university that specializes in agricultural research, and I work for a company that specializes in agri-technology, but I'm not a farmer, not even an agronomist. So I'm a bit anxious in talking with farmers and telling them how I can solve their problems. But when I talk with farmers in horticulture and dairy and viticulture and others, and they tell me about their challenges, as a scientist, I think what they're describing are systems of inputs and outputs, and they're trying to optimize it. And as a scientist, this is the kind of thing that I say, well, I can understand this, I can apply technology to it. Next slide, please. I look at a farm like this and I think, what are the inputs and what are the outputs? Please. For example, on the input side, farms get sunlight, rainfall, nutrients get applied, feed, lots of things. Some of these inputs you can really just measure and monitor, like sunlight and rainfall. There's really not much you can do to control that. Other things like feed and nutrients, irrigation, the application of other things, they lead to management decisions, and these are the things you can control and optimize, and that ultimately lead to some kind of an output, a yield. Whether it's fruit or milk or meat, the analogy will hold for whatever you're farming. Obviously, I'm simplifying farming quite a bit here. I realize there's a lot more going on, but thinking of it in this way leads us to an optimization problem that you can understand and solve with technology. And as someone that specializes in computer vision and machine learning, this is the way I would tackle a problem like this. Next slide, please. So the question then is, what would we like to measure? What can we measure? And if we've measured it, how can we appropriately act on that information to actually turn it into a valuable decision that leads to an optimized yield or an optimized outcome? For example, what would we like to measure? Yield is an obvious one. You can measure and monitor your yield as it grows or as it matures, and this gives you an indication of what it's going to look like at the end of the season, things like milk, fruit, or juice. You want to know if you've got pest and disease. You want to monitor and look for incursions. You want to definitely notice evidence of infestation. You want to know what the health of your animals or your plants are, which includes deficiencies in water and nutrients and things you can change about their diet. You want to measure the current productivity of whatever you're farming with or growing. You can look at growth rates and everything involved with that. These are some examples of things that you would like to measure, and some of these things are easy to measure and monitor, and some of them are not. But data on its own isn't very useful. You have to do something with it. Next slide, please. So once you've measured this, what kind of actions can you take to actually do the day-to-day optimization of your farm, which would lead to your ideal yield and outcome? Examples include things like irrigation, it's adding an input, and the question is how much, when, and where. Same with spraying of herbicide and pesticide, when and where and how much. In horticulture, pruning and thinning is a really important task. It involves quite complex decision making. The question is, again, when do you do it? How do you do it? How much, where? Fertilizer and nutrient application is another example, similar to irrigation and spraying of herbicide and pesticide. The question is when and where. So in answering these two parts of the optimization problem, you can apply machine learning and computer vision in both of them. And for the rest of my talk, I want to show some examples from projects that I've been involved in on how we used computer vision and machine learning to tackle these two kinds of problems. Next, please. One of the early success stories with computer vision and machine learning is object detection in images. You can use this for all kinds of applications. In this example, we wanted to count fruit in fruiting canopies. Instead of sending a bunch of workers out into your orchard and manually counting, which is expensive and takes a lot of time, we just take a lot of pictures and train a model to count the fruit for us automatically. So the image there on the left is called an activation map, and it tells you a little bit about how the model is actually treating the image and making the decision. Activation maps illustrate what part of the image a trained model activates on. And this model was trained to activate strongly on apples. And so you can see red boxes and blue boxes. And the red boxes represent where in the image the model is activating strongly. And you can see it activates strongly on apples, and it doesn't activate strongly everywhere else. And so that, if you process that map, you can get something like the image on the right, which indicates where all the apples are, and you can count them. And as I mentioned, you can apply this to lots of different applications, not just counting fruit. Can I have my next slide, please? For example, this is exactly the same kind of technology, the same activation map, but in this case, we apply it to flower counting. So you can see this model activates strongly on the parts of the canopy where there are flowers. So you can do something like a flower density map or even a leaf area index if you've trained the model to activate on leaves. Just another example of the same kind of idea. Can I get my next slide, please? This is another example of the same thing, a slightly more sophisticated model. This model was trained to identify and count inflorescences in grapevines. The inflorescences are very small. They're, in fact, like proto-grape bunches, very, very small, immature grape bunches. But the model highlights them, as you can see on the slide there, and is able to count them, which can give a viticulturalist or a vineyard manager a very good indication of yield very early in the season, which can be very valuable for them. Can I get my next slide, please? We can also use computer vision and machine vision for other more complex applications. In this example, we use it to combine two different kinds of sensors, so you get the best of both worlds. We were approached by seed companies that grow ryegrass, and they wanted a machine that can non-destructively, quickly and accurately estimate the biomass of a plot of ryegrass. But to make matters more complicated, these are typically mixed swards, so they contain ryegrass and clover, for example. And the seed company wants to know what the ratio is of ryegrass to clover, exactly how much of that biomass is clover and how much of it is ryegrass. And they want to measure this daily, efficiently, and without affecting the way that the grass grows. So what we did is we started with a sensor called a LiDAR, which is a laser scanner. It has the ability to measure the above-ground biomass very accurately, but it just gives you a volume. It doesn't differentiate at all between ryegrass and clover. So what we did is we also added a color image, a color camera sensor into that same patch of grass. You can see the color image example on the top right there. And then we train a model to segment that color image because it can recognize the clover leaves from the ryegrass leaves. And it can segment every part of the image as either being a ryegrass or clover. And that segmented image example is shown on the bottom there. So if we combine the segmented color image with the LiDAR biomass scan, you get not only an accurate biomass estimation of the grass and the clover, but you also get the ratio of biomass to clover. So that's another interesting example of how we can apply computer vision and machine vision to tackle the measurement problem of my introductory slide. Can I get the next slide, please? To this point, I've really just focused on different ways of using clever sensors to measure your inputs. But measuring the inputs and not doing anything with the data is useless. I also want to include an example of how you can use the same kind of technology to actually do decision making. And the example I'm focusing here is on automated cane pruning. So imagine you're a pruner in a vineyard, and you get given a vine like this, and you're told, pick, say, 2 canes, one to tie down on the left, one to tie down on the right. Pick an appropriate number of renewal spurs and prune everything else off. And that's the task that pruners have to do every season. It's a critical task. It's very laborious and intensive and expensive to do. If they get it wrong, it can not only affect the yield for the current season, but for many seasons in the future, because you're actually changing the structure of the canopy. It'll take many years to recover from a bad prune. So it's a very important task. It has a large effect on the yield, but it also involves complex decision making, because good pruners know you can't just pick the thickest cane or the healthiest looking cane and tie it down. You have to make sure that you're not crowding the vine head. You have to make sure you're not creating a situation that's difficult to harvest later on. And sometimes you also want to say, well, this could be a really good cane to tie down this season, but I should keep it for the following seasons instead. It'll be more valuable in the long run. So a complex problem. The next slide, please. So imagine that you've already solved the problem of measurement. This is actually part of a larger project that we work with several colleagues in different universities across the country. I even see some of them in the audience here. So imagine that we have a sensor, and this is being developed currently, that can scan the vine and give you an accurate 3D representation of everything you need to know in the vine, like the image on the left there. The image on the left is actually a 3D reconstruction, a 3D point cloud of a vine. And from this point cloud, you can extract the thickness of every cane. You know where every cane sits in relation to every other one. You know where the guide wires are. You know where the vine head is. You have all the information you need to make good pruning decisions, but you still don't really know how to interpret that to make those decisions. Because ultimately what we want to do is send those decisions to a robotic arm, like the one on the right there, which contains a custom-built pruning device that gets guided to the right cane and can prune it off or leave it there. And what we need to develop is the bit that sits on the inside between those two images, the thing that makes a decision based on the inputs data and can either then guide a robotic arm or help a human pruner to make better, more efficient decisions. Next slide, please. So because I said I specialize in machine learning, I train a model to do this. I take the input, I show the model examples of the output I want, in other words, labeled pruning solutions, and train a model. The problem is, to train a model like this requires that you ground truth your inputs data with good pruning solutions. We want to have a model that can learn how to prune from only examples. Trying to teach the model to prune based on a set of rules that are often ambiguous and can be very subtle, and also is quite difficult to collect because pruners don't always agree and there are lots of different philosophies. Instead, we want to say, can we teach a computer about pruning just by asking an expert pruner, tell us what the correct pruning solution here is. Show the system lots of examples of this and prune it in that way. Problem is, you need thousands, tens of thousands of examples to train a complex model like this. And collecting the scanned data as well as the labels from the expert pruners will take several seasons and be very expensive. So what we did as a first step is we said, well, we're going to train on synthetic data. We're going to generate synthetic vines using technology that you often find in video games and CGI movies that can generate realistic-looking trees and vegetation. We generate these vines, and the advantage here is that we can generate as many of them as we want, thousands of different kinds of varieties and random canes everywhere. We control each and every part of that vine. We know where all the canes are. We can generate them any way we want, which has advantages in diversity. And when you train your model, you want diversity in different kinds of vines. It also has the advantage of we can show these vines to expert pruners and they can label them virtually. They can actually sit behind a computer instead of walking through a vineyard and say, well, if I saw this vine in real life, I would prune that cane, and this one, and I would tie these ones down, which greatly accelerates the speed at which we can collect the knowledge from the expert pruners. So this is an example of an early prototype model that we trained, and it was able to identify which canes it thinks should be pruned off and which canes it believes should be tied down and which canes it believes should be kept as renewal spurs. The red ones indicate canes or spurs that should be pruned off. The green ones are renewal spurs, and the two yellow ones are the bearer cane. So obviously this is a two-cane pruning system with one bearer cane on the left and one bearer cane on the right. My next slide, please. So those are my examples. In summary, I said that farms can be modeled as systems of inputs and outputs that need to be optimized. The question is, what do we need to measure? How do we measure it? And then secondly, and just as importantly, is how to act on those measurements. Now, at this point, I wish that my talk was actually first, and Seth and Remy spoke after me, because this is exactly what they were talking about, is how you use the data you've collected on your farms. It sometimes feels to me like a lot of research is going on to building better sensors and more sensors and less expensive sensors, and we're collecting massive amounts of data on farms. And often it feels to me like what it's doing mainly is being stored, and it ends up being useful to researchers, not farmers. So actually tackling the second half of the optimization problem, which is using the data you've collected, even though turning that data into valuable actions and optimizing your outputs that way is often an overlooked part of current research, and I would like to see more of that kind of thing. So if I have a take-home message, it would be, if you're a farmer, go to your local industry body and find out what they're spending their research money on, and make sure that at least part of it is also in using the collected data to automate or to make some decision-making tasks more efficient and better. Thank you.
Jacco, thank you very much. This was interesting. I've been sitting on the edge of my chair taking a lot of notes. And first we had Seth and Remy, and they started to tell us that sustainable landscapes are multifunctional, and they're combined visualization and science, so that they can actually map the current state of the land, then identify land use opportunities, then come up with recommendations, and then hopefully then by combining the visualization with gamification, the user is getting enthusiastic and saying, yes, let's plant some trees or let's grow some tulips. Tulips, Seth, right? Yeah, tulips. Tulips. Jacco basically looked at farms as systems, and Jacco made a very, very clear point that, of course, generating data to support that decision making is really important. So measure, model, and manage. He showed us many examples how vision technology can actually help us making those decisions, and he is using computer learning to actually create the decisions for on-farm, the tools for on-farm decision making. And he challenged all of you to make sure that there is more research being done or more investment being done in that area. I think with that I've summarized the talks, so everybody has all the talks fresh in their minds again. So I want to open the floor for questions, both online and in the room. There is Joe will come with the microphone to you.
Hi, Richard Green. Yeah. Hi, I'm Richard Green, University of Canterbury. Thank you all to the three speakers for really interesting talks about computer vision as it applies to farming. I guess I have a question for Seth and Remy. So clearly computer vision infers you're imaging the environment to make decisions, and you mentioned that a 1 metre by 1 metre resolution was too high a cost, and you mentioned Sentinel-2, which has sort of like a 10 to 60 metre range. So obviously this comes down to cost for a return on investment and how much information you're getting. At the moment, I mean, we know that things will get cheaper and cheaper as people are throwing more satellites up there with better sensors, and perhaps eventually we'll have autonomous drones flying everywhere. But at the moment, what did you find the optimal resolution was in terms of cost for what you're trying to get out of the images?
Do you want me to answer that? Yeah, Richard, are you in the room or? Oh, all right, all right.
I was hiding around the corner so you can see where that's where.
It's quite weird, I say.
The world is.
So from my perspective, I think we had an era of apps. We then had an era of IoT, and the IoT era everyone said everything will be connected and everything will be that, and you go and ask anything and it will be given, right? And I think the IoT crowd have turned into the interoperability crowd, and I think there's still a thing of, hey, we're going to link everything and it's all going to be great. I guess what we learned is you've got to ask yourself what you're linking and why you're linking it, and exactly what you said, what's the return on the effort, essentially, for linking those things. I mean, there's some obvious things that we haven't touched on in our presentation that perhaps should be linked when you look at some of the pressures that are coming to farmers from farm environmental plans. But if the objective is to send a prescription to a VRI on a pivot, use that quality data. But if it's, am I going to grow apricots or peaches? And really what we're trying to do is get people onto that bandwagon of change. We're not going to try and give them the answer, but get them onto that bandwagon of change. The precision that's required is significantly less.
Yeah, I'd agree with all that. I'm looking at 0.1 millimetre scanning large areas, hectares of vines and things out with petabytes of data. But my question was the large, huge areas you're scanning of countryside where there's no way you can afford the cost of planes with LiDAR and imaging and so on. So you said that 10, what was it? It was, you said 1 metre by 1 metre was too expensive.
Yeah.
And using Sentinel, which is the range of whatever it was, what did I say? 10 metres to 60 metres. So what did you find was, like a good resolution for your return on investment, for what you're trying to do for those vast areas?
So the Sentinel one will probably end up being an input layer as opposed to an operational layer. One of the trade-offs is that the higher up you go, you can never diversify from your goal. So, so more information in a pixel gives you more flexibility. So at the moment we're operating at a 1 hectare reporting scale for nitrogen, for instance. Sediment, we move from a 1 metre.
So for sediment, we move from a 1 metre to a 10 metre, but we are reporting the result at the 1 hectare grid level. And this is also because on top of what Seth has said, I think we started with the bias of scientists to go deep into the precision and try to understand the perfect picture of something, where actually the people that we were talking with and delivering to were not expecting this level of precision. And they were excited with the good map. Like a 1 metre map is very good. You can see all the gully and see precisely what is happening there. But at the end of the day, they don't make the decision on this level. And so we came to the conclusion that an hectare would be good at the moment for them to make decision. But we also work with try and error type of approach. So we might be wrong. I think to give a final answer, we don't know. We don't really know, but we make assumptions and we try to see what is working best. And at the moment, the 1 hectare grid is much better than the 1 metre one.
Thank you.
Thank you so much. May I have another question?
Also a question for Seth and Remy. I was just wondering in the future how you envisage the tool, the visualisation tool being made available to farmers, how they would actually use it, how they would get access to it. Would it be through the farm environment planning process, or can they do it from their kitchen table, or how would you envisage that working?
So we've got a real desire for this thing to go into the public, because we've got a lot of stuff that sits on our shelves that never leaves our offices, and we've learned a lot in doing that. And some of the things there we were saying with Richard, it's not it's a science tool, but it's not a science. It's not a. I haven't written a paper in the last year, right? And so it's trying to find a solution as opposed to academic excellence. We're learning a lot in that process. We don't think that this is the be-all and end-all. We think that this is provides a particular component of, for instance, the farm environmental plan picture, which is, people being able to interact with existing models that are particularly hard to interact with now. So there's definitely a commercial vent that we're driving. We would like to see it out in potentially the next 12 months, and it would be possibly coupled or integrated into an existing product. Does that answer the question?
Yes, I think so. So you're thinking of it going out through like farm consultants or that sort of. Is that what you have in mind?
So this particular version of the tool is best suited for farm consultants. Yep. So, yep.
There's another question there, Joe.
Yeah.
Do we have any questions online, Katie? And then, I would stimulate the people that are watching us online to post the questions in the chat box.
Hi. So, like Richard Green, I'm another computer vision person, not an agri person. I have a couple of questions, so one for each of the speakers. First for Seth and Remy, the issue around generating maps from underlying data. So you showed the example of the maps of the appropriateness of growing a certain variety of apple and of growing Sauvignon Blanc grapes. There's a couple of kind of issues that really come to a head when doing that in mapping. And so the first one is the sort of machine learning truth, which is that they're really good at interpolation and they can be really, really bad at extrapolation. So you have a bunch of data points, but as you say yourself, not a huge number. You generate a map over the whole of New Zealand, and the problem is people look at a map and they go, wow, that looks beautiful. But the question is, for all the areas where you had no data, how can you be certain that it's actually accurate? So is it producing a beautiful map of something that's not actually really very accurate? And related to that is people will look at a map that's been drawn in high resolution and immediately assume that that's the resolution of the certainty of what it's trying to present. And I give the example of your map showing green for growing Sauvignon Blanc grapes on the eastern side of Banks Peninsula, which I was kind of wondering whether that was actually really doable. And so the question comes down to, again, how do you ground truth the entire map when you've done something at national scale? And at what scale are you expecting people to actually use it? If I have a farm in O'Kane's Bay, should I be looking at the map and going, cool, I'm going to grow Sauvignon Blanc? Or is that actually taking the map too far?
Sure. Do you want me to start?
Yeah.
So I think there is several aspects of the question here. For the validation part of the question and validating the maps, we've done two things. So if you consider the current land use map for apple and grape, we essentially selected a catchment near Nelson, and we have the full photo interpretation of the catchment. So we manually photo interpreted all of this catchment, and so we have an extensive validation of what we have produced there. And we are not dependent on a small amount of validation point with this extrapolation issue. Sometimes it's not possible. It's very intensive to do this photo interpretation process, and not that useful because essentially we don't want to do that. This is why we are developing those models. And for the grape and the apple maps, like the land use suitability maps, what we've done is we have worked with experts that are validating the maps. So we have the data validation with a database and a limited amount of points to validate the outcome of the models, but we also go to experts and the industry and ask them if it is relevant for them or not. So that's a second level of validation that might be more relevant at a national scale in order to cover some aspects that are not captured by the databases. And regarding the resolution, what we are doing is essentially we are very transparent. So we try to not produce maps that are very fine resolution without having this resolution backed by the data, the original data. So the land use suitability is working on a 1 square kilometer grid. So you won't pick the very small microclimates, for instance, and we are not pretending we can do that. So we are very clear. It's really, I think, a transparency question there. This is also why we report the result at a 1 hectare grid level, because we don't want to go too deep into the precision and give a false perception of certainty, essentially.
Okay, that's very good, thank you. And for Joko, I guess it's a similar question around the example you gave of pruning the grapes. I'm interested in how you sort of estimate the accuracy of that. Do you go back to the experts and say, here's a bunch of prunings that were generated, can you rank them according to whether you think they're good prunings or not? Or how do you determine how good the model is?
Yeah, we definitely need to go back to the experts. As I mentioned, because it is so expensive and difficult to collect the expert data, we tend to keep the expert data for testing purposes only. We typically train our model on purely synthetic data and maybe just fine-tune it on a few expertly labeled pieces of data. The advantage of training on synthetic data is you can actually make up a pruning rule and automatically label a large amount of data. Now, I started by saying that it isn't wise to assume that you can do pruning based on a set of rules, because pruning is such a complicated process and because there's so much subtlety in it. We always revert back to the experts. But there is value in saying we have developed a model that can learn to prune based on a set of rules, and therefore, even when those rules are not known, even when the rules are hidden by the experience of an expert pruner, we can still use the same model to train to prune as that pruner would have trained based purely on those pruners' examples. And if you want to score it properly, then absolutely. You go back to the expert pruner and you say, this is what the model thought. Do you think this is correct? And that's how we would score it in real life.
Okay, cool. I might just add one suggestion to that. I've done some work in areas where it's virtually impossible to get a decent amount of training data because it's just too hard a problem. And one of the ways that you can often apply to that is show the expert 2 examples from synthetic data or from your model and say, just tell me which one's better. And they can really, really rapidly give you a whole pile of those, and that gives you some training information.
Yeah, we will look at that definitely. There are things like semi-supervised learning, and there are semi-automated labeling approaches as well, where we will train a model to do a pruning, but the model isn't very good. It's not trained very well, but it generates a lot of almost perfect prunings very quickly. And instead of then asking the expert to take a fresh synthetic vine and prune it from scratch, we just say, this is a half okay solution from the model. Is it good, or would you change anything? And it's much faster for that pruner to say, this one's good, this one's good, this one's good, now I'll change that, than actually starting from scratch. So there are ways of accelerating it, but it's still quite expensive.
Thank you so much. I saw there is a question here. There is also a question online, so we'll have the question online first and then we'll come to you. Is that okay? Yep. Thank you.
This one has come from online, but it does seem to be on a similar vein to the question that you've just answered. This one's for Jarkko. In developing the model canes to train machines in large data, how do you account for the variables of those model canes that are not known? By that, I mean, in a similar economic farm model developed to determine nitrogen use on profitability, the model did not account for growth rates of grass, so the outcome or decision was completely wrong. How do you shortcut AI learning using models that give certainty to future natural growth patterns of grape canes?
Okay, well, I would say there is no such thing as a perfect model. It would be unrealistic for us to think that we can ever extract all the metrics from the vine that real pruners extract from them. We've spoken with expert pruners, and they'll tell you that when they look at a vine, they look at the color of the cane. Is it a healthy cane? Is this cane growing in the right direction? Is it thick enough? Is the origin of the cane low enough down the vine head so that it won't break when I tie it down? Things like that. But in reality, they almost subconsciously look at lots of other stuff as well. They take into account how the season went. They take into account what they think is going to happen next year. They take into account the neighboring vines, the lay of the land, all kinds of things that would be very difficult for us to measure even if we knew about it. So we simplify the problem to the best model that we can, and we are going to miss things. The model is not going to be perfect. The question is it good enough to make the decision-making process for the pruner more efficient? Is it good enough to help them make a decision faster or more accurately more often? And eventually, maybe, we can get to the point where it becomes so good that you can automate that process. And even if it'll never be as good as the real expert pruner, it'll be, hopefully, a lot cheaper. So there's a trade-off.
Thank you so much. Question here. You get a microphone, sir.
I think those two questions somewhat sort of address my concerns as well. But what I was trying to understand is that I don't know much about machine learning, but I have dealt with the models in the past for a number of other projects. So my question is that as you said, no model is perfect. But what you are saying is the machine learning model also same, right?
The machine learning model also...
Also not perfect.
Yes, yeah.
So in that case that, now usually the conventional models that, we know what are the assumptions that we use for modeling, and then also we understand what are the risks associated with those assumptions. And then we do sensitivity analysis in order to understand that how we are going to interpret this information to wider crowd. So you are following the same process when you are doing machine learning as well?
We'll get to that point. It's fairly early in the project at the moment, but you're right. Some mistakes are more expensive than others. Some mistakes are riskier than others. If you have a cane that has a lot of shoots that are all fairly similar, and you decide, I'm going to tie this one down, but I could also tie its neighbor down, and they're both sort of okay. There's no clear way of saying which one's better. If you take the left one instead of the one next to it, and the expert tells you, well, actually, I would have picked the one on the other side, that mistake is not as bad as saying, I'm going to prune both of them off, and I'm going to take this one completely wrong on the other side instead. So, yeah, we try to mitigate risks so that we, in those cases where we want to be really certain about a pruning decision, the model is designed to be risk-averse. It wouldn't say this needs to be pruned if there's a high probability that if you make a mistake here, it's going to be a large cost. Having said that, these are things that we're planning. It hasn't actually been tested or built into the model yet. At the moment, it's a fairly simple model. We extract 5 or 6 metrics from the vine, or actually from each cane in the vine. So it's quite a simple input to the model, and the model just takes each cane in relation to all the canes around it and decides, should you be pruned off, should you be kept as the left bearer or the right bearer, or should you be kept as a renewal spur?
Thank you so much. There is a question in the back.
A question for Seth and Remy. Just on we know that we're going to see, well, we have seen more extreme events in terms of climate. And I'm just wondering, with the work that you're doing, obviously you alluded to that with the Sauvignon Blanc and where you might be growing that in 2050, but also, can what you're informing, farmers potentially now, looking out that far ahead, saying, well, actually, we're going to see a higher rainfall here. You really might not be farming the way you're farming now, purely because that, sediment loss is going to be a big issue for you, or some other variable that, or management issue is going to arise because you're going to see more of these extreme events.
Yep, to a certain extent we can, but as you and I both know from our previous work, a lot of that, say, sediment or phosphorus is lost in single events. What we're not particularly great at is capturing single events. So the future forecasts give averages over a month, is it? Yeah. And also things like hail. We can't predict hail, which is a big thing for horticulturalists. So they're things that we're sort of working on, but certainly where you're looking at, long-term annual rainfall, yes, we can do that. But I guess that's also complicated by how that water's allocated and managed as well, which obviously sits outside what we can do.
Yeah, I guess I was wondering, if we know that the frequency of those one-off events is going to increase, and each one of those events might be generating, 20% of your total sediment loss for 1 year or 5 years or something, whether there is still the opportunity to kind of integrate that into a model, but, I'm just not sure.
Yeah, I think there would be.
Yeah, I guess like what Seth explained about the geospatial grid and combining all of these different variables to provide outcomes for the decision making could be used here. So essentially, we might not have the resource or the skills within the small team currently to deliver this type of models, but the framework we are developing can certainly handle this type of questions. So we can, for instance, talking about sediment, have an erosion risk map that could be plugged into our solution and show those areas.
Thank you very much. Do we have any more questions online? We don't have questions online. Any questions in the room? There's a question up here, Joe.
Yeah, question for Jacko. Is it just far too expensive to have a photographer following along an expert pruner doing before and after photos to build a data set?
Well, just having before and after isn't always enough. One of the things that we find quite difficult is if you look at a vine before pruning, you've got canes growing randomly in all directions everywhere. And then after pruning, it's extremely neat. It's got the vine head, and it's got, if it's a 2-cane prune system, 2 canes coming out of it, and that's it. And now you have to figure out those 2 canes that were tied down, which one of these random mess when you started off with do they actually relate to? We found that the fastest and easiest way to do this kind of labeling is just tying flags to all the canes and having a pruner come and say the red one and the blue one, the other ones I'm tying down. The other reason why we don't usually do it that way is we don't want the opinion of just one pruner. We found there's a lot of diversity in pruning strategies. Even with expert pruners, they generally don't agree on how to prune a particular vine. So what we'll do is we want to prune in a non-destructive way. We want to have the expert pruners come and say, looking at this vine canopy, I would take this one for the right cane, this one for the right cane, I would take this one as a renewal spur, and the rest I'd take off, and then he leaves it. And then the next one comes, and then he looks at the same vine. And that way, we can prune non-destructively.
Thank you so much. Any more questions? There's...
Yeah, Jaco, I just want to follow on from that question. If you've got multiple pruners coming in and they're making decisions around the, this seems to be almost, it's not as objective as you might think, it's almost subjective. So how does the model take those, what are really subjective opinions on which canes you keep, which ones you don't, and then how are you combining those?
Yeah, that's very true. The model does not deal with subjective things. It knows it's a correct pruning solution or an incorrect one. That's all it deals with. But the process itself is very subjective. And if you talk to wineries and vineyards, they'll sometimes tell you things like, well, our pruners have been pruning this vineyard for many, many years, and it's actually part of our brand now. The way that we prune, it may not be optimal, it may not be like our neighbors are pruning, but it affects the quality of our wine in a unique way, and this is how we prune. And so often you don't want to prune correctly, often you want to prune like they prune. So you need a system that learns to prune like this very special, valuable pruner that's part of the winery's brand rather than saying, well, according to the latest research and according to the best pruners worldwide, the optimal way to prune this vine is to do this, this, and this. And they'll say, well, okay, fair enough, but that's not the way we do it.
Yeah. Well, it depends what you're pruning for. You're pruning for quantity, which a big producer might just want, big yields, average quality wine, and smaller producers might want
I've had that conversation before. I haven't really met many ones that would admit to saying, we just prune the best that we can. It can be mass pruned and done cheaply, and the wine that comes out is of quality that's good enough to sell.
Yeah.
Is it also possible that the opinions might, the theory of opinion, is it also possible that while their opinions change, they end up making the same pruning decision at the end, like for doing it for a different reason, but end up still tying that one and still tying that one?
Yeah, it's totally possible.
Well, ladies and gents, thank you very much. If there are no more questions in the room nor online, I want to thank the panel very much for being here. And looking at the number in the audience and the level of the questioning that we got, definitely thank you very much. You got us thinking, or modeling, or interpreting, or at least we will visualize it, hopefully. Katie, may I have the next slide, please? Moving on from this, we will actually have a Vibe Series event looking at machine learning and how that can transform the X sector. That will be on the 18th of August. You are very welcome. And we are looking at the next innovation series, Giving the Land a Voice. So look online, keep up with our events. You are very welcome to join us either online or in person. The Vibe events are in person. We also have a co-working space. So if you are looking for a desk and you want to work in a very nice environment, come and try us. First day is on us. And I thank you very much for being here, and I hope everybody gets home safe. Thank you.